Good morning, everyone. Once again, welcome back. Now, today I'm gonna continue with some new concepts. These things were not available in the past in my lecture notes during this uh, offline or online learning process. I was able to prepare these things for you. To tell the truth, they are relatively a little bit higher level with respect to the things that we have seen about optic flow concepts. Now, today I'm going to talk about two very important things. One of them is the visual tracking concept, and then using motion models to how to make tracking. The second part will be extra for you. You are not responsible in the midterms. I will just try to briefly explain what it is, but the most of the part today I'm going to talk about the visual tracking and those well-known discriminative filters and a few examples about CME's networks as well. Okay, let's start. First of all, let's talk about the fundamentals. By the way, I have a new thing. Maybe you are realizing I'm gonna write here to my notes. Therefore, you will be sometimes able to see my drawings or my notes as well. Okay, now let's first of all define what is a visual tracker or what's visual tracking. It's the obtaining the trajectory of the moving objects in time from a video frame, for a video sequence. Slightly different from optic flow because it's only considering two consecutive frames, but here I'm talking about just trajectory, therefore it's relatively more difficult. And obviously we need a model because we are doing something in time. Two things change. Obviously the motion trajectory is changing and also the appearance changes. Therefore, we need a model on the appearance while we are tracking something. Okay, maybe in the beginning it's something else, and typically in the beginning, a bounding box selection by a user is the typical input. Therefore, the user will select which target to track, and then the algorithm will continue in that way. And then there could be a motion model, and finally, using these two things, we will search this appearance model based on this motion model in the next frame where this object is. This is called the tracking, and we continue online in this form. Obviously, the fundamental thing for any kind of tracking or optic flow estimation is matching. Okay, we have to make a visual match. Obviously, the objects are also changing in time. It's not that trivial. Okay, the template matching is a very robust fundamental technique. You can call it as match filtering or whatever with different names than signal processing. Okay, the template matching is basically taking a template, maybe a user selected target image in the frame one. In the next frame target image, you are just looking everywhere and you simply take the difference between these two things or just multiply as a correlation. And you try to find where this 4x4 template matches on this target image. That's our aim, okay? There could be many different techniques to do it. And moving the template over the target image and correlate with different positions, you could have finding the peak value among those correlations. And for every shift, we obtain a result as a result of this correlation or convolution. That's called your response value in the correlation plane. Therefore, what we are saying here is we take this, make a correlation between them, and then we basically obtain a result. Shift by one, we repeat it. Shift by one, we repeat it. And for all these values, whenever it has a peak, that peak is a strong indicator that that template is in the correct place where the matching between two consecutive time instants could be achieved. Okay, therefore that's a very fundamental technique. This is an inevitable technique. The optic flow algorithms, the KLT for example, also basically depending on these kind of concepts. Now let's try to improve these concepts. What are the problems of this simple template matching? Okay, first of all, you have a slight change in the pixel location. Instead of this, for example, that point, you just move one pixel to the left or to the right. The result, your output response of the correlation should not affect drastically. Okay, once you have the perfect match, you have a beautiful result, a strong ping, everything is other than this is smaller, or vice versa. Okay, this is not shouldn't be affected drastically as soon as you move just single 1 pixel to the left or right. Okay, and moreover, if your appearance is also changing in time, slightly non-rigidly changing, then your peak still should be sufficiently high with respect to its neighbors. Okay. Uh, the second thing is there should be an algorithm. We should be able to update the changes of the appearance, the visual appearance. Okay. Therefore, the target is moving, changing, and I have to have a way of changing this information very efficiently and robustly. The third thing is translation. Well, in here, within a search window, you can look for this template. Okay, you can look for this template, and within the search window, you can look where it is. But then there should be a search window. Or you can do the same thing in a very fast way in the FRIA domain if you make the circular shift without moving anything in a search space, which is typically done in the next slides. We will just move the intensities in a circular manner, and we will just look for where is the best way to find this template. In all these things, please note we have a restriction. We have a restriction about the how much the object can move between frames, and it's a translational motion with a circular shift if you are using Fourier transformations. That's also a little problem that we have to tackle with in practice. Another thing is if you move towards the camera or far away from the camera, your size will change of the target. Therefore, your appearance update is okay, but in the meantime, you are looking not for a 4x4 in the next frame, maybe with a 4x4, you will try to match a 5x5, 6x6, since the object is getting larger, for example. Your algorithm should be able to work with those kind of scales. And instead of raw pixels, raw images, nowadays you have to be able to use multiple features together. Okay, there could be multiple features coming from different feature extractors, and your algorithm should be able to combine them. Computation is very important. Typically, these algorithms work in real time. Therefore, you have to use some multiple feature maps. Still, you have to have real-time performance, and you have to do some tricks to improve the performance. And finally, you have to be very accurate. Okay, therefore, you could be try to obtain a very good tracker, but maybe it's just basically the bounding box is moving back and forth. Therefore, this is something we don't desire. We always would like to have a very good accuracy. Now, the above problems, they are tried to be addressed with different techniques in the literature, but there is one group of algorithms called discriminative correlation filters, in short DCF. Those DCF and the family of filters during years, they try to attack these problems one by one and try to solve all of them up to a point. Okay, let's see how these things work. Well, what is the main idea? Again, we are just matching, combining, or correlating two image patches in two different frames, and we are trying to look their visual similarity. This could be achieved for different goals, not only for tracking. If you're trying to detect an object, if you're trying to recognize an object, you also look for similarity between image patches, but let's assume we are doing it for the tracking right now. Okay, the concept is this: if they coincide, if just put on top of to each other in the correct place, there will be a high correlation. Otherwise, it will be a low correlation. That's the idea, okay? Now, please note at this point, such an approach will work very well if the appearance of the target does not change significantly. Okay, if it changes, then there could be some problems that we have to deal with. Okay, and another thing is, it is a heavy computation. You are just shifting by one for an n by n template. There are n square pixels. You take the differences or multiplications, you add them up, you obtain a single value. You just shift by one, you do it again. But in the Fourier domain, since this is a convolution, correlation is nothing but a convolution, it is simply an element-wise multiplication in the Fourier domain. Going to the Fourier domain is n log n, okay, or n squared log n squared, okay, for our case. Therefore, that should be relatively easy, okay, and we have to have relatively a computationally easy job to do it. But please note at this point, from now then, I'm not gonna shift my template on the next image by a simple displacement to the left or right. I have to do everything in a circularly shifting manner, because all the rules about convolution and multiplication in the time domain, in the frequency domain, is only applicable when you have a circular shift. Therefore, we have a one little drawback. From now then, if we do anything in the Fourier domain easily, we should always remember that we are not moving our template anywhere, but we are just moving, we are shifting it circularly so that we can make the matches very fast in the Fourier domain. Okay, now the amount of shift, the unknown displacement in the next frame, is stored in the DFT phase. We have already seen this concept. Okay, but this time the circularly shifted version of the discrete image, because everything will be on DFT, and the DFT requires circular shift to be able to use its convolution property. Okay, now let's write the aim. We will have a very small number of training data, training template, maybe your past 10 frames, maybe just a single one. I'm going to obtain a single filter. I'm going to obtain a summary of all these things instead of all the training data. That will yield the maximum output at the correct displaced position. Okay? Therefore, I'm going to have a summary of my past and filter and training templates, maybe single one, maybe all of them. But at the end, there will be a single filter. That single filter will look in the next frame wherever your correct displacement of the tracked object. Okay, this is called, such a filter is called, because such a filter will handle the correlations in a very discriminative manner. Therefore, this is called discriminative correlation filter. It is making a correlation as a filter, and it is not only making a correlation, it is doing it in such a way that all the training data will create a very discriminative space with respect to all the others while we are trying to detect the target. Okay, now that's an attempt going back to 80s, and in the first things there was no training. Okay, they were people just trying to recognize an object, find an object using some training data. The same idea. A single filter, a single representative will help us finding the position of the data at a new input. But now we will just apply these ideas for tracking purposes. Let's start with the first algorithm. That algorithm is not for tracking, but the idea is very simple here, and we will use this idea during tracking as well. Now, an ideal correlation between an image patch and its circularly shifted version has a single beautiful ideal impulse peak in the correlation plane. If you take an image, if you make a circular shift to the left 5 pixels, you will have in the correlation plane, which is only a single impulse at 5 pixel shift, all the others will be relatively small, or if it is a zero mean input, it will be completely zero, okay? And we will just try to find that single peak in the Fourier domain, okay? If it is circularly shift, I don't have to just do this computationally heavy operation in time or image domain. I'm going to go to the frequency domain. I'm going to take the DFTs, and I'm going to just simply look for the response, okay? Now, in practice, the peak strength, how high the peak is, obviously it could change because the targets visually changing, their appearances are changing. It could be slightly unpredictable, okay? Now, the idea here is very simple, but it's a very strong, beautiful idea. Instead of using an ideal impulse peak, try to obtain a Gaussian shaped response. In other words, find me a filter so that when you make a correlation of two circularly shifted images, at the correct shift, I am not expecting a perfect ideal impulse, but a Gaussian shaped response. In other words, this is the Gaussian shape, and what I'm saying is this: hey, I'm gonna have trying to find an output g of xy, which will be completely specified for every training data according to the shift that I know. This is a training data. And what I'm going to do is I'm going to take the correlation between the training image, f of xy, and the filter, unknown filter that I'm trying to find, h of xy. I'm going to just make a correlation, a convolution between them. Then I want this response to be a Gaussian where the peak is correctly located at here. Because this is a training data, how much shift I did, I know it, and I'm just putting my Gaussian to that correct position. That's what I'm saying. I know this, I know my F, I am trying to look for an H. Please note there were two images. This is one of them. The other one is not given. The other one is just giving us the information of the position of the peak. And that H will give me a filter which is capable of generating not an impulse, but a Gaussian shape. Now, the desired filter can be obtained in the Fourier domain very easily, if assuming that everything is circularly shifted rather than a simple shift. Therefore, the convolution and the correlation has a little difference. Therefore, for convolution, these are multiplication. We know it very well in the 2D frequency domain, omega and nu here. But in correlation, we have to put an with an extra conjugate here. This is the H conjugate. Hence, we will have nothing but the G is obtained in terms of F and H conjugate, and the unknown filter response in frequency domain will be nothing but your Gaussian shifted at this position according to the correct shift divided by your original image. Okay, beautiful. Let's finish. This is the filter using a single data whose shift is circular shift is known. We were able to obtain in the frequency domain nothing but our filter. But how am I going to use this? Just a single filter. Is this division will create a problem because there could be some zeros here that could make us going to infinity. Now the trick here is this. Let's use multiple filters for each training sample, which means your previous shifts, okay? Because we have coming for maybe multiple time instance, or here, if it's not a tracking problem here, in fact, you have multiple samples of the same data whose positions are shifted a little bit. But we know all of them because they are training data. We will obtain those filters for every such different training data, and we will simply average it. Hey, why do I average it? We can assume that this is like all of them are like a little classifiers, and making like weak classifiers by making an averaging like a boosting operation, we are just improving their detection performance. Okay, or can assume that such an averaging process also is basically removing some noise, and that's one simple extension that we can do. Now, let's see what we are trying to do. This is your first image. That's the eye detection problem. And I'm going to just put on the left eye, okay, on the left eye, this eye, the position where it is, I'm put a simple Gaussian of this form. This xi and yi is nothing but this position here. For this guy, I put another Gaussian. For that eye, I put another Gaussian. They are not at the same positions. Now, if you take the Fourier transformation of these things, and if you divide them, G transformation to F transformation, you will obtain nothing but H transformation, which is this guy. And if you take the inverse, if inverse Fourier transformation, In the frequency domain, in the image domain, you will obtain this H response. Another H, another H. Do you see any I here? No. But look at this result. If you just take the average of these three training samples, nothing but the average of these things. If you take the average of them, since Fourier transformation is a linear operation, in the time domain, you can also take the average. If you sum them up and divide by 3, this is the result. While you are summing them up, please note that you are just putting them to the correct position. You are just put their origins to the correct positions. If you sum them up, okay, you will obtain nothing but this filter. Now, the I filter, which is trying to detect these things, were not visible in the beginning. But here, now we are obtaining an average I filter, and this I filter is getting, at the end, something visible to our eyes as well. And those shifted Gaussians, although in the beginning they are not visible, right now we were able to obtain some results out here. Okay, this is our very simple averaging synthetic filters, and by the help of these filters we were obtaining some filter which is giving us a very intuitively acceptable result. Now I obtain a single filter from multiple data which is creating an impulse, but not an impulse, a Gaussian shaped impulse. That Gaussian shape is helping us to obtain some robustness between different views. And this kind of an averaging is also eliminating the problem with having zero divisions here, because you are taking lots of different averages, and those averages are basically removing any frequency where the division is equal to 0, and you obtain a beautiful result where you will be able to obtain, or you will be able to correlate good eyes during your detection. Now, that was the very fundamental concept. That's a beautiful idea. Now, that idea is basically applied to a first tracker as called MOSE, minimum output sum of squared error, in 2010. And basically, that's a discriminative correlation filter concept applied to tracking in the first place, okay? And this is the first algorithm which is achieving that. Now, obviously, we assume that the initial target position is provided manually, or some other algorithm detects it. Okay. Now, ASF or ASAF algorithm requires many training data to obtain your frequency response of the filter. It's a little bit too slow for tracking. It's getting for taking many DFTs, dividing and just taking averages. It could be slow. Therefore, we have to do another algorithm which will be improving this slowness. But the problem here is if you take a single data between two frames, then the element-wise division in the frequency domain is unstable. It could go to infinity. Therefore, we don't prefer that one as well. And then we do a little trick here. Instead of simply dividing to obtain the filter, let's write in this way. In the frequency domain, everything is in the frequency domain. These are frequency-wise multiplications. And this is the G function, again in the frequency domain. We are just simply minimizing this difference. We don't say they are exactly equal, but what we say is this multiplication at a particular frequency and subtracted from the same frequency of the Gaussian squared, maybe it's by the way it's magnitude square, because that could be complex. Okay, that square sum for all the data and for every training data that you are using, maybe a few of them, that should be minimized with respect to H. This unknown H, the unknown filter, this time is obtained not simply dividing by, as we did before in ASAP, but we are just trying to minimize this one. Hey, minimization of this thing can be obtained by simply taking the derivative of this thing with respect to H conjugate and for a H conjugate for both of these frequencies, omega and nu. Okay, for every individual frequency, we have to take the partial derivative of this thing and then equate to zero. Okay, if you do so, this difference is the magnitude square and sum for every sample or training data we are using. If you take it, please note we have to do such a thing because we have to have this kind of a term. There will be four terms like alpha minus beta, alpha minus beta. There will be like this. Okay, there will be four terms, beta h, alpha, it goes on like this. It will be alpha h beta and finally beta h beta. Okay, we will have these four terms and those four terms are here. If you take the derivative with respect to one of them, okay, which is h, you will see that, for example, that term will bring these three guys here. Those two guys will be here. In order to take with respect to h conjugate, you have to take the first conjugate and another conjugate, and you will have fg conjugate from that one, and finally that will be 0. And the result, the optimal frequency response, becomes nothing but this one. Okay, this result is fg is these guys here, and this we are having these three terms. If you just take into the parentheses of h is independent of the frame index because h is constant for all frames. We are just obtaining a summary for all frames. This h will be nothing but this result. Okay, this is a simple notation that's showing that element-wise division and element-wise multiplication you will obtain for every element in your h, and that's the resulting thing that we obtain. Okay, therefore this is our final result that we have. This is our optimal filter. Mosse is using this filter, but the only concept here is, hey, should I use every time, do this from the last 100 frames, 10 frames, 5 frames? During tracking, we have to do something else so that will be a good update in time. They used a little trick to make it online. The trick is this. Hey, this h is consisting of a numerator and denominator. Let's assume like an IIR filter, okay, like this. We are like having a y of n minus 1 plus 1 minus alpha x of n, okay. Let's assume we have like an IIR filter, but this IIR filter, it's working in the numerator and in the denominator independently. This is the numerator part, and that numerator part is getting the current value, this x of n here. Okay, just maybe let's make it alpha and 1 minus alpha here. Okay, therefore this part is this part gi fi is this part, and this is our previous result in the coming from during the iterations. In the previous frame you did this, and numerator and the denominator basically getting the two terms, and they are independently working, and they are working like an IIR filter, and they are updating II and BI values appropriately and continue in this way. Okay, therefore we are making such a filtering state, and that will be improving the computation a lot. You just only do a single DFT multiplication and just nothing but adding the previous value by a factor of a learning factor, which is giving like an importance. The last data is more important with this much, and the previous data is less important with that much. That was the Mosse algorithm. That was a very beautiful, elegant algorithm. It gave very good results. That's like a little breakthrough in the literature from tracking purposes, and with a very fast time, we were able to obtain some good results. Okay, now let's look to our DSST. Okay, the DSST is is giving us another algorithm, maybe the most important problem in all the trackers and also MOSSE, the scale changes. I have an n by n template. The object is no more n by n. It's getting smaller or larger depending on the motion. And then I have to do something so that I can take into account the scale changes. How can I do it? Okay. Therefore, I have to do something so that an n by n and maybe n plus 1 by n plus 1, how can you match those things? Now, and another thing is, uh, in 2014, now people were using, instead of raw data, multiple features. How to combine these multiple features together in a fast way. Now, I'm going to first tell you about how to combine these things. Then I'm going to tell you how to solve the scale problem. Let's start. Let's extend the MOSSE. MOSSE was working very well, but how do you incorporate D number of features with T number of training data? This is the original MOSSE formulation. I'm just writing in a different notation. H is for only a single T, there is a, for every instant there is a single filter. These are our past training data. This is the positions of the correct positions in a Gaussian shifted version, which is written like that. And I'm trying to write this in this way, okay, which is this is time domain or image domain. This is the frequency domain. And you obtain this result, which is the previous result that we obtained. Now, assume there are D features which are denoted no more with F, but F superscript L. This L shows D number of features, and I need D filters. Every feature domain has a different filter, but this time the response is constant. Okay, therefore, for a single instant, whatever your feature is, the correct G, this response, should be at the shifted position. This is the unknown shift. But in the training data, we know the location of the shift. Now, if we write this thing, if we extend this time for a single T I'm writing, by the way, for L1 to D features, HL, for every feature there is a filter. This is the feature. They are convolved, subtracted from a single response, because the response, the position of the target is fixed position. We know it. There is a single for time. But I did do a little trick here. I put a regularization term. I also add saying that, hey, in the frequency domain, my response, the support of it, the energy of it should be low. I don't want too many coefficients. I don't want a very long support. I will prepare a relatively small support. If you do the same thing, take the derivative of this thing in the frequency domain, just like here, and obviously using Parseval's formula, this is nothing but the h magnitude squared here. If you do so, if you take the derivative and equate to 0, as before in the previous slide, you can simply obtain very easily nothing but this solution. Okay, this solution will bring extra lambda here, and the good thing is that lambda will help us to eliminate this zero division problem, by the way. Therefore, we understand that regularization is working in that purpose as well. Putting a regularization term here, you are basically getting rid of this unstable dividing by zero kind of problems. And the rest is nothing but the same. The previous IIR filter, ALT, the numerator, the denominator, the numerator, the previous value, and the current value, and you obtain the same thing as before. Okay? Now, this is the regularization term that we have here. This is basically removing the problem of zero frequency components. And what we do is, at every next frame, I calculated this ZL. ZL is nothing but my intensity of the next frame for feature L. I just multiply with the frequency response of feature filter L. There is, please note, there are D filters. These are D filters that we have, and those D filters I just multiply with the correct filter for the L feature, and we take the inverse Fourier transform, and that will give me a maxima. That maxima is my possible position in the next frame, okay? And now what I'm gonna do is I'm gonna just add all these things to each other, okay? I'm gonna add all these things to each other, and at the end, please note here, this summation is L1 to D. For filter 1, filter 2, filter D, I'm gonna multiply with the corresponding Z's, and I'm gonna add them up, and I'm gonna obtain the final response for multiple features that I'm trying to obtain. Okay, but please note once again, uh, if this is your current template, there are L filters. In the next frame, I am looking to the same position. If this point is 100 and 100, the corresponding thing in the next frame is also 100 by 100. I assume circular shift here. Therefore, if the guy moves from here, there's an object here, it goes there in the next frame, okay? It is making a circular shift, hopefully, okay? And then in the next instant, this Y response will have a peak. This Y will have a peak at 0, 100 by 100, okay? Or if it is moving 150, it will be the 50 location, 50 by 50, okay? From 100 to 100, we move to 150 to 150 in a circular shift. Therefore, this is origin here, assuming this is origin. You move to 50 by 50, and this is the position of your next data. And you obtain it through the nothing but the whole features. Now, how did we do the scale invariance? Frankly, there is no very interesting solution. We obtain a scale space representation, a pyramid, just like for every different scale, we are having +5 and -5 different scales here, okay? And we are increasing by 1.02 at every scale and the reciprocal of 1.02. In other words, starting from here, I have okay, I have this, a smaller version, a smaller version. In the meantime, a larger version. It goes on like this, and then I obtain a larger and the larger versions. In this way, I am just testing. I am just testing my results with respect to these smaller or larger objects, okay? Therefore, what I'm doing is basically obtaining the image, the next frame at different scales and try to make matches. If your object is getting larger, you will be able to obtain with a larger scaled version, the matching will be improving. Therefore, after finishing the correct position, target location through this, then using different scales, you checked whether the output value is maximum along these 5 large, 5 small, different total 11 scales, okay? Therefore, we will just look to the highest confidence, highest response, and we will say that that scale is my correct scale. Therefore, in the next frame, if my current bounding box is 100 by 100, in the next frame, it will be 102 by 102 because this is the correct scale. Let me continue from this point. Okay, now that concludes our DSST algorithm. By the way, there is a famous video object tracking challenge. DSST was the winner in 2014 for this approach, and it gave very good results at that time. Now, in 2015, in fact, the previous people, the people from Linköping University, led by Martin Danelian, they come up with a different algorithm called spatially regularized discriminating correlation filters in 2015, in short SRDC. They attacked another very fundamental problem. Until now, I was just simply moving in the same frame. There is nothing like a search window, no search window. I am having a single same position with the assumption of circular shift. Hey, my object is a very small head maybe here. If it moves like that, I cannot find in the next frame where it is, isn't it? Because it is only capable of finding the displacements within itself. Then the target that you are trying to find, if it moves a little bit higher than its own size, there will be a problem. That's a very important issue. And by the way, they try to solve this using a mask filter, which is basically weighting the filter that we are estimating in an appropriate way. Let's see how it is. There is a special regularization component W. That's a map, that's not a scalar. Okay? It will be introduced to penalize the filter coefficients according to their locations. Okay, let me explain what it is. This is our original DCF formulation. This SF is nothing but F and the image X is convolved or correlated. Okay? Therefore, filter is F right now. X is the data, maybe a feature. T domain, training data. And alpha is right now, just assume it's like an impact parameter of the training sample. Okay, at k, if k is 1, this is the nearest sample, for example. If t is the furthest away sample, the importance getting smaller and smaller. Just assume like that at this point. Okay, yk is our Gaussian. This is the Gaussian. This is the convolution. This minimization we have to achieve. And in the meantime, the regularization table of the filter, again, for every such different features, D, we are doing it. Please note this is also having for different features, okay? Now, the concept is this. Let's change this one by inserting a weight filter in this way, okay? The only difference between these two is here. This filter is multiplying with an regularization component, okay? Therefore, a special term. This is this term. If this green box is your target, but if this guy is moving the head a little bit high for a large displacement, then you cannot be able to find it by only considering the green box DFT. If you take the green box DFT, you can only find the shifts within the green box. But if you make your window larger in this way, and if you put such a term which is giving high values in the peripheries, low values in the center, as here, therefore this filter will change itself so that it will not only make this correlation minimum, it will not try to make this thing minimum, but it also tries to take this term to be minimum. Hey, this is fixed. This is given initially like this. This is like such a fixed deterministic filter giving high values in the special peripherals. Therefore, the only way for this filter to be minimum is to make the corresponding filter coefficients here to be small. Otherwise, these things will make large values together, and that will be not a minimization. Now, what I did is a little trick here. I enforce my filter not only make good correlation, but also have a regularization and also to have small values with this new enlarged window, target window. Okay? But the problem here is this. Previously, there was a beautiful closed form expression here. Now, In the image domain, I have a multiplication. What I'm going to do with that? This part was okay. I just know obtain a beautiful solution in frequency domain. It's fast. But what I'm going to do with here? Well, in order to improve the execution time, still I'm going to go to the Fourier domain. I'm going to show the Fourier domain parameters with the caps. Therefore, this term is the good old term. I just simply have term by term. These are x cap and f cap. They are multiplying in the frequency domain. Y cap is the Gaussian Fourier domain correspondence. Okay, it's still a Gaussian again. And here, that was a multiplication in the time or image domain. It will be a nothing but a convolution in the Fourier domain. Okay, therefore I have to do something here. I have to do something here, and that multiplication in the time domain will be a convolution in the frequency domain. Okay, therefore that filter, which is fixed, all these parameters are given in the paper. Okay, this is just like this kind of a reversed Gaussian type of a shape. Okay, like a inverse bell shape. That filter convolved in the Fourier domain with this corresponding unknown F filter. Now, unfortunately, I cannot take the derivative equate to 0. I have to do something else. First of all, any convolution operation, okay, x of n, y n, which is x of n, y of n minus m, okay, such a thing for m is 0 to n minus 1. You can write this thing as, if they are fixed number of available things, this is like x1, x capital N minus x0, and you can write these things like y0 and the shifted versions. This is yn minus 1. You can have a matrix like here. This matrix multiply with this one is basically such a convolution. By the way, this convolution is, I just show it in general, this convolution is right now in the frequency domain. I just show it in the time domain. But instead of this convolution, I'm just writing this kind of a result here, okay? And this convolution is written in terms of matrix, okay? That's the previous thing that we have learned, okay? This is nothing but the previous thing. I just write, instead of inner product, I write it like an inner product with like an x vector and the y vector. You can write it like an x0, x1, diagonal xn minus 1. Like this is y0, yn minus 1. These are all zeros. This inner product is equivalent, this diagonal matrix. This matrix is nothing but, this matrix is nothing but the diagonal. In the diagonal, we have x cap k, the Fourier transformation of the input data, and we have this result. Now, from this point on, the rest will be based on optimization. Not simply taking the derivative and equate to 0. I have something to be obtained in terms of minimization with respect to f, and let's see how can we achieve this. This is the previous thing from the previous slide, okay? Now, one little thing, I am working in the frequency domain. F cap is frequency domain. I will obtain an F cap at the final result, and this F cap should give me real valued coefficients, okay? Therefore, I need some real valued coefficients. I have to have an auxiliary enforcement, okay? I need a symmetry. As you remember, x of n real, then we have x e to the j, omega becomes the real part, and the magnitude is even, and the odd, the imaginary part of x of n is odd, okay? We have this fundamental property from DFT and on DTFT, and this symmetry will be enforced by the help of a matrix. In other words, you are saying that uh, you are adding your appropriate entries of your DFT in such a way that this resulting thing is symmetric. Therefore, that symmetric thing will give you for sure real data. Okay, therefore, what I'm doing is by the help of a B matrix, which is simply adding the appropriate coefficients to enforce symmetry here. And the introduction of this matrix obviously makes B here as well. And also this matrix will be multiplied from left and right with this B and B Hermitian. And this new cost functions will bring you such a term rather than this one. Now I have this term. This term is basically nothing but our in previous formulation like in Mosse, just enforcing with some symmetry in the Fourier coefficients. But there is this thing right here. This W is okay. This W is the block diagonal, which each block diagonal is equal to the C matrix. Okay, and you can write, if you take the derivative with respect to f tilde, you can still obtain like AF is equal to B kind of a solution from here, where this is equal to this one and B is equal to that. And in order to improve the computation, instead of having this closed form expression, which is giving you a very large matrices and dealing with these matrices is very difficult, instead of having this matrix inverse, we prefer an iterative Gauss-Seidel method just for an optimization approach. But in fact, this result is obtained through this kind of a thing. And if you have sufficient large memory, you can find the result. But for a real-time performance, we will prefer to have this Gauss-Seidel performance. And at the end, again, the result, that result, can be written as using such an update equation, okay, as before. This is the AT minus 1. In time, I'm multiplying with the past value. AT is obtained with the past value of AT minus 1, and this result as the current relation. Similarly, B is obtained in the same way, and that gives us the final results. Now, in the standard DCF, if you give such a area, target area, the resulting filter will be something like this. With this kind of a formulation, by enforcing the peripheries to be zero, you obtain such a smooth, beautiful, specially regularized result. That is the result that we obtain through SRDC method. The original previous formulations are giving like that. There are lots of small components and some large components, which is in especially not very regularized homogeneous. But here I obtain a much smoother result by the help of this extra term here. That extra term is helping us to give this result. Okay, let's stop here at this point and let's give a break. After the break, I'm going to continue with the new trackers.